Okay, the last 15 minutes of class today, we're going to do our first lecture quiz. So to start today, anybody have any homework questions? Okay. So the first one, this is in the math preliminaries, number 8. And the equation is 5t squared x double dot is equal to 50 where x of 1 is equal to 2 and x of 10 is equal to 20. We can solve this by separation of variables. So we get x double dot is equal to 10t to the negative 2. And now we can think of this as, so x double dot, that's the second time derivative of x. We can think of that as d dt of x dot, okay, is equal to 10t to the minus 2. And now separate variables and you get that. So what this is an infinitesimal increment in x dot, okay? Like the variable is x dot. You could also think of it as, you could think of x dot as some new variable, z or something, okay? And then it would be dz dt, and you could use separation of variables and then substitute in for z. But I think, to me, it just is easier to just think of this dx dot as just an infinitesimal increment in the variable x dot. Okay, just think of that as a, yes. Yeah. And this is equal to 10t to the negative 2 dt. And now you can integrate. The integral of dx dot is just x dot. And that's equal to negative 10t to the minus 1 plus c1. What's different about this problem from, did you have a second derivative before? Yeah, the one right before was a second derivative. Number 7 was, but the difference with that was you had a boundary condition for x dot and you had a boundary condition for x. So for number 7, at this point, if you wanted, you could use the boundary condition for x dot. This one, both boundary conditions are x, so we can't do anything yet. All we have to do is set this aside, okay? And now we'll use separation of variables again. Dx dt is equal to 10t to the minus 1 plus c1. And so dx is equal to negative 10t to the minus 1 plus c1. And you can integrate both sides. Okay, so you get x is equal to Um, so this is negative 10 natural log of the absolute value of t. We're only dealing with positive times. We never have negative times, so I'm going to leave out the absolute value here. This is just ln t plus c1t. And now we have a new constant of integration. Okay, you with me on that? And this is our second equation. And now we can finally use boundary conditions. Okay, so how are we going to do this? Well, the boundary conditions, let's do them one at a time. The first one says when t is equal to 1, x is equal to 2. So plug these into the boxed equation right above. 2 is equal to negative 10 natural log of 1 plus c1 plus c2. Okay, so log of 1 is 0. So we have c1 plus c2 is equal to 2. Okay. So this is the first problem where we see this. We go through a boundary condition and we can't solve for anything. So how are we going to do this? Back into the second. So yeah, exactly. So we're so in these cases where both of your boundary conditions are on the dependent variable itself, you don't have any that's on the derivative, you have to solve it as a system of equations for your constants of integration. Okay, so this is the first of a system of equations. So yeah, the way you're thinking of it is just right. I'm just going to set this aside, solve the other, come up with the other one, and then solve it as a system. So the second boundary condition says at t equals 10, x is equal to 20. So plug these into this boxed equation. You get 20 is equal to negative 10 natural log 10 plus 10c1 plus c2. Can someone tell me what's 20 plus 10 ln 10? 43.03. Okay, so that's our second equation. And this is a small system of equations, 2 equations for 2 variables. You can just do it by substitution. But what if you had something like this and it was a big system of equations for a whole bunch of variables? The way to do that, we just talked about it yesterday in statics, is to set up the augmented matrix for this system of equations and then use reduced row echelon form. So I'm going to set up this matrix that has 2 rows and 3 columns. First column is the coefficients for our variable C1. The second one is the coefficients for our variable C2. And then the third is our constants. These have to be These have to represent the constants alone on one side of the equation. Well, that's how I set them up here, but you have to make sure that that's done. So for the first equation, we have 1C1 plus 1C2 is equal to 2. The second equation says C1s, we have 10 of those. C2s, we have 1 of those. And the constant is positive 43.03. If you'd done this by substitution, you would have been done a long time ago. But substitution is not what you want to do if you have a system of 10 variables and 10 equations or more. Can someone give me the answers to this? What? Yeah. So now that you have that, do reduced row echelon form on this. And it gives you this new matrix. That's 1's in the main diagonal, 0's there, and your answers are in the last column like this. And I think all your calculators have reduced row echelon form as a built-in function, so you can solve systems of equations like this. Okay, 4.56, negative 2.56. Okay. And then plug that back finally into our expression for x. So negative 10 ln t plus 4.56, what was that, t? Minus 2.56. And that's your final answer for x as a function of t. Any questions about that? Any other homework questions? Okay. Okay, so this one says x dot y dot is equal to t squared 0, 0 t times xy. And the boundary conditions are x at 0 is equal to 1, and y at 1 is equal to 10. This is a system of equations. You just have to know how to multiply out the matrix and the vector on the right side. So to multiply this out, you take the rows of the matrix and do a dot product with the column vector. And the answer to each of those is the element of the output vector. So the dot product of t squared 0 with xy is t squared times x plus 0 times y. And the dot product of 0t with xy is 0 times x plus t times y. And so that comes out to be t squared x ty. And now that we have it in that form, we can see that that's an uncoupled system of differential equations. It's uncoupled because x and y stay in their own equations. And that means you can just solve it as two totally separate differential equations. So we have, one differential equation, x dot is equal to t squared x, a second one that y dot is equal to ty. And that's a pretty easy pair of equations to solve by separation of variables. Any other homework questions? Okay. Okay, let me do one example. So let's say that so this is going back to the chain rule stuff in kinematics of particles. So let's say an object moves along a path y equals x squared in the direction of decreasing x. With a speed that changes as the thing moves along the x-axis, and the function is x squared plus 1. We want to know what's the acceleration as a function of x. And then we're still doing kinematics, but while we're at it, let's say if the mass is 1 gram, what's the net force on the object as a function of x? So calculating the net force, that's kinetics. We're not really on that yet, but I just want to point out why do we care about the accelerations of things? The reason we care about accelerations is almost always because accelerations are the gateway to knowing stuff about forces through Newton's second law. Okay. All right, well, let's draw a picture of what's going on. So here's the coordinate system. Yeah, net, yep. Okay, so it's traveling along this parabola in the direction of decreasing x, which means it's going this way. So how are we going to go about this? Well, the first thing we have to do is figure out the velocity vector as a function of x. We have the path and we have the speed. So we just need to use the path to figure out a unit vector in the direction of motion. And what does that look like? Well, if we're here on the path, a unit vector is always tangent to the path. So that's the direction it's moving at that instant. And we just need to come up with an expression for a unit vector that's tangent to the path in the direction of motion like that. And then, so what we want is the velocity vector as a function of x. And that's equal to the speed, which is a function of x, times the unit vector, which is a function of x. Okay, we already have the expression for the speed. We just need to come up with the unit vector. So to find that unit vector as a function of x, first, the position vector as a function of x, we can represent as x squared. Okay, that's called a parameterization, the parameter being x. The function that it's traveling along is, okay, so the position, vector is the vector xy, okay? And we were given this function, y equals x squared. So I just put x in for x and x squared in for y. Yep. And so now a vector that is tangent to the path, a vector that's in the direction of motion at any instant, and I'm going to call it u. It's not going to be a unit vector yet. It isn't going to have a length of 1, but it's in the direction we want. Is the derivative of each of these two components with respect to whatever your parameter is. Okay, our parameter is x, so this is dx for the x component, dx squared dx for the y component. And so that's 1, 2x. And now we have to come up with a unit vector. Wait, one more thing. So if this is our, this is the direction we want, what we just calculated was a vector that's in the direction tangent to the path in the direction of increasing x. So we have to multiply this by -1. To deal with the fact that our particle is actually moving in the direction of decreasing x.
Should I already understand why dx squared over dx is not dx? Is it 2x?
Okay, is not just, okay, so all we're doing is, we have our function is x squared. I think you just haven't seen that notation maybe before, but it's just the, if you take, so if f of x is equal to x squared and you take the derivative of that function with respect to x, then you just use the polynomial, derivative. Yep.
I'm going to get kind of concept mixed up.
Yeah.
So a few days ago, you were saying not think of velocity as a derivative of physics and those kinds of things.
Yeah.
But yet, it just seemed like you're just doing the derivatives of these.
Okay, yeah. Okay.
Know what I mean?
Yes. So here's the underlying thing so if you have a position vector expressed as a function of any one parameter, so that's what we call a parameterization. And let's call this parameter, let's just call it S for now. It's just anything. It doesn't have to be X or Y. It can just be any variable. Then the derivative of that position vector with respect to that parameter is tangent to the path in the direction of increasing parameter values, or S values, I guess I can say. Okay, so whatever that is, whether it's X or Y or whatever the independent variable is, if you take the derivative of both components with respect to that parameter, the vector that comes out is tangent to the path in the direction of increasing whatever that value is. Yes? Yeah. You have both of them expressed as functions of that parameter. So like, for example, you could have the position vector be S cubed negative sine of S, okay? And we don't even have to know physically what S is. They're both expressed in terms of the same parameter. And that means if you take the derivative of this with respect to S, you get a vector that's tangent to the path that it's following in the direction of increasing S values. Well, yes, if you're doing dynamics, then it's always a function of time. I guess, if you're thinking of it as a path, then yes, it has to be a function of time. But this is also true in math if you're just thinking about a function. If you represent, so mathematical functions don't change over time. It's just a function. But if you represent a function in terms of a parameter S, then this will still always give you a vector that's tangent to that function at any S value. Yeah. Yeah, that's easy enough. Right. Okay, so this is an aside. Okay, so now we have this. So here's how we are. Here's where we are. We used the fact that this is parameterized by X, took the derivative with respect to that parameter, multiplied by -1 because we're going not in the direction of increasing X, but the opposite direction. And we have this vector that now for any X value is tangent to the path. It's in the direction of motion. It's not a unit vector yet. So we need to make it a unit vector. And to do that, we'll calculate the magnitude of that vector, which is, -1 squared plus negative, what was it, 2x? Negative 2x squared square root. And that's square root of 1 plus 4x squared. And then the unit vector is -1. The unit vector is 1 over the magnitude times the vector u. So that's -1 over the square root of 1 plus 4x squared. -2x over 1 plus 4x squared. And so now the velocity vector as a function of x is just this times the speed, because this is a unit vector in the direction. And so all we have to do is multiply by the magnitude of the velocity, which is the speed, and we get the velocity vector. So that's v times this unit vector, which is negative quantity x squared plus 1 over 1 plus 4x squared, and then -2x times the quantity x squared plus 1 over 1 plus 4x squared square root. Okay, now we have the velocity as a function of x. I mean, probably the single most noticeable thing about it is we started out with a pretty simple looking thing, something moving along a parabola with a pretty simple relationship between the speed and the x position. And when we express it as a velocity, we get this pretty ugly looking thing. But now finally we're at the point where we can say, we can use the chain rule and say that the acceleration as a function of x is equal to the derivative of the velocity vector with respect to x times dx dt. So that's dv dx times the x component of the velocity. So that's this times this value here. So that's negative x squared plus 1 over that square root. And I'm not going to go through this here. I mean, you can see that this is messy. But you're going to take the derivative of that velocity vector with respect to x, okay? Which that's obviously like a really painful derivative to do by hand. I mean, pretty painful derivative to do by hand. It's not the most horrible thing in the world. But if you're writing a program or something to do this, Mathematica can do that derivative for you. Your calculator can do that derivative for you. I don't care that you know how to do that by hand, but and what you have then is the acceleration of the particle at every location along that curve. And then the last step that I mentioned, so what's what's the net force acting on that particle? Well, Newton's second law says F net is equal to the mass, so 1 times 10 to the minus third kilograms times the acceleration. And so you know what the force is that's applied to that object in each one of those instances. Any questions about that? Yep.
So the derivative of x with respect to time.
That's right. Well, yeah, you have to be careful if the whole problem is done as a function of y, say, then you have a dy dt, and dy dt is the y component of the velocity. But that's just based on the definition of velocity. Velocity is always the time derivative of position. Okay. Any other questions? Okay, let's do this quiz.